So we are inside this order finding algorithm. So once more we are given an N and an A, and we want to find the order of A with respect to N. Yes. The order is denoted by R, and we have this relation MA suffix A, psi1 equals this we already had the last day, and so we realize that given the A, if we are able to find out a way to implement the phase estimation algorithm where this MA is the unitary, we wrote down what this MA is, and the corresponding eigenvector psi1, then we can find the R. But then we realize the trouble is that psi1 itself contains the information about this R. So although we may be able to create the MA, but we may not be able to create the psi1. So instead of that, we took hold of the state 1, which is an equal superposition of all the eigenvectors of MA up to from 0 to R minus 1, and we took the setup that determines the phase of the unitary MA corresponding to one of its eigenvectors, but instead of putting in that eigenvector, we put in the state 1. Yes, this was where we ended on the last day. Yes. So, a priori it is not clear what this will give us, because this 1 is not an eigenvector of MA. So, there does not exist a phase like this, of this form. So, the phase estimation algorithm, as we have learned, it is not clear what it will give us by putting the 1. So, this is what we want to see, and we realize that the state that comes out, this also was done the last time as far as I remember, running the phase estimation, quantum phase estimation on 1. On 1 means in the lower part, this lower gang, we put the 1 instead of it was supposed to be an eigenvector, but we put in 1. And the unitary that we are using is this MA for this estimation. The state immediately before the measurement on the top group and dumping of the second group is this. Yes, it's just the linear for given psi k. It gives me a phi k psi k. So when you have the 1 put in, which is exactly this, gives me phi k psi. Yes. Any question up to here? Otherwise, we will go forward. But these psi k are orthonormal, yes? You can check that by looking at its explicit form, or you can realize that from the spectral theorem that this is a normal operator, a unitary operator, so its eigenvectors are orthonormal, so orthogonal, and we have normalized it. So, the probability to obtain some value j from the measurement there is a measurement that is done on the top group. When the phase estimation is run with 1 as input, I mean, there is the auxiliary part that is the product state that is put in on the top part. So that is always the input. Here I am talking about that 1 as input instead of the eigenvector. Yes? Is just the average over k belonging to 0 up to r minus 1 chosen uniform. Yes? These are orthogonal. You trace them out, you get an equal mixture of them. This is true, right? When you have anything, any alpha 0 plus with equal coefficients, it can be plus, minus, or whatever, and some beta 1. So this is some, so in our case, this is the part that will be dumped, and this is the part that will be measured, and these are all normalized, and 0, 1 is equal to 0. There can be several terms. I'm stopping at this term, and there can be some phases here, but the modulus of them are equal. Yeah? So you can put in whatever you want. So, so here it will be 1 over root 2, and then here you can put some e power I alpha 1 and e power I alpha 2 and so on. Yeah, if it will change depending on how many terms are there. Now, I'm not assuming anything for the inner product of alpha and beta. They could be non-orthogonal. But if I trace out these two, I will get an equal mixture of alpha and beta. The phases will all vanish. This is half because there are two terms. If there are 5 terms, we will 1 by 5. Yes, this part is done. So if you trace out an auxiliary part, which are orthogonal terms, it will be an equal mixture of whatever is there. So for example, if you have, let's say, 0, 0 plus 1. If you trace out these two, you will get an equal mixture of 0, 0 and plus. This is, by the way, that is running in the channel in the B92 protocol. You know the B92 protocol? Okay, so we come back to our algorithm. So the point is that if we are dumping a part, it means it's tracing out. So we are tracing out this part. Here we have an equal mixture of them. And so an equal mixture means you can assume that they are coming with coming randomly. Yes, so you can pretend that in the phase estimation algorithm, in the phase estimation circuit, the states that are coming are these states, and they are coming randomly with equal probability. So is just the average over K, and we have measured the value, this is this J, so you can just pretend that it is some psi K, and you are trying to find out the J. What is the probability of the J? Because you are measuring the J at the end.
Are you simply saying that probability of getting that J is sigma J phi K mod square, sum over K?
That will happen in a very simple case. Here, of course, the entire circuit is a much more complicated
So
one.
assuming that
The whole, whatever the probability that you get if psi K was put in, that probability has to be averaged over the K with equal probability. Whatever the probability comes, that has to be averaged over the K uniformly. Yes? Write it again. So now, let us consider the problem that use phase estimation to show, phase estimation problem to show that if the unitary that is used in the phase estimation algorithm is MA and the state that is put in the bottom group of qubits is psi k, we can find k over r with significant accuracy. We have done this problem for the psi1. This is the same thing here. There it was 1 over r. Now it is k over r. This implies, well, I will not do the problem. You know it, I am guessing. But this implies that using 1 as input in the phase estimation algorithm. Again, I mean, when I say 1 as input, I mean the bottom group, yes? The top group, there is a 0 tensor and before the other one. We are talking about, that remains the same all the time. This implies that using 1 as input in the phase estimation algorithm gives us an estimate for k by r with this chosen uniform. So let us see where we are standing. We needed R, or what is the same thing, 1 by R. We have found K by R with K uniformly chosen at random from here, yes? Well, this sounds like I need A, and after all this I have found AB, A multiplied by B with B unknown. This sounds like we found nothing, yeah?
One go, yeah.
But we will see that we actually have found the answer. But that will come later, but up to here, what it will give us, we will see. But make sure that this statement is clear that we agree with this. Why we want that is the next question. Questions? Comments? So to go further, we have to consider some new terminology once more. There is something you may already know, that there is something called the continued fraction algorithm. I mean, the classical algorithm. Something in arithmetic. It gives us a way to do the following thing. Given any real number, call it alpha, and it's between 0 and 1. And an integer m that is more than 2 or equal to 2 there is at most one fraction x over y with integers x, y such that y doesn't touch 0, of course. And they don't have a common factor. And mod of well, just beside every real number there is a close to any real number there is a rational number. But there is a method for finding that. cost, so I will not do the algorithm, but we have to again be careful about there is not a hidden exponential inside it. The cost is order of log m cube. So there is not a high cost.
Given alpha, we are trying to find x and y.
So we will use this fact. So we go back to the phase estimation algorithm, where we have run the algorithm with 1 as the input. So we run the phase estimation with 1 as input. We get this K by R with high accuracy. We know how to increase this accuracy. With K uniform in on yes. We now run the continued fraction algorithm for K by R or some m, choose an m. Suppose we get this equality is in this sense. It's equal up to this. Up to this much. This still does not give us the R because the K is still unknown. But the Y that we get here divides R. We'll get two numbers X and Y. Whatever that Y is, it will divide R. Yes? Because of the way this continued fraction algorithm runs. Call it y1. Run the phase estimation again with 1 as input. And now this time, this 1 cannot be reused because the state that came out of the bottom group of qubits is not the same as the input anymore. It is not an eigenstate. So you have to create the 1 once more. We will thereby get a y2 that also divides R. If this sequence, if the sequence that is generated thereby this y1, y2, this is long enough, the lowest common multiple of the yi's with high probability. Integer factorization algorithm, let's find the problem of finding the prime factors of an integer, which is the problem that the Stoll algorithm solves. Is equivalent. I mean, it can be shown to be equivalent to the will not do this. This is another set of arithmetic. There is no quantum mechanics inside that.
Here, we are trying to find an approximation to k by r. You're saying it's we are finding a fraction that is very close to k by r, but we don't have k by r. We have some k dash by 2 raised to n. If we had used n qubits, first phase
Why?
distribution algorithm.
Why 2 power m? We have
Because
k by r.
K by no, we are when we use phase estimation algorithm,
Mhm.
we get some k by 2 raised to m as our phase.
We have a
If we have n qubits in the phase, like if we had used n qubits there initially,
the output of the
But-
top bits is some j by 2 to the power m, which is close to k by r. With
which
high
is close to
probability.
the phase we are trying to find. So we are not finding k by r, we are getting some k dash by 2 raised to m as our phase, which is very close to k by r. So now we are saying that that k dash by 2 raised to m is also close to k by r, and we are also saying that x by y is close to k by r. How is that possible? Either will
If two numbers are close and if another number is close to, then the first and the third are also close.
but then
This is the
the
triangle
theorem
inverse.
said that there's only one fraction which is very close to k by r.
वो GCD पे limit है. तो x और y को double कर देगा तो same number ही मिल जाएगा.
Like मैं ये बोल रहा हूँ कि अगर k dash by 2 raised to m k by r के close है,
वो कोप्राइम नहीं होगा. जरूरी नहीं है वो कोप्राइम.
कोप्राइम बना दे.
तो x by y मिल सकता है ना.
तो we don't तो फिर ये इंटीरियर algorithm यूज करने का मतलब नहीं था.
So, you have any other questions?
पता नहीं है ना initial
Yes.
कोप्राइम है.
Why cannot we use like one again?
कोई
Because
तो
we are
generator कोई integer
tracing out the last one, and then whatever operation we are performing is on 5Q.
Yeah, that is true. But the thing that you are tracing out is not 1 anymore. Because it is not an eigenvector. So you remember that the state, this time when you put in the 1, that the state that you get is this. What was the name? It was phi k psi k. It was like this, yes? So this is not 1. It's a mixed state. It's actually an equal mixture of in the space of the psi k. It's highly mixed.
Sir, when you wrote long enough,
Yeah, so this is still sloppy in terms of the epsilon delta. It can be made more. You want to ask that question?
yeah, when will you stop?
Yeah. So it essentially depends on the difficulty that is there in the capital N. So the thing that we are trying to factorize, trying to find the order, factorization will come later. This can be made more. So it can be made more. So the main thing that I wanted to tell you is that we have to be careful that we have not hidden any exponential anywhere, so that everything remains polynomial in the whole. So here there could be an hidden, but it is not there. So, but you can think that maybe you have to run it an exponentially large number of times. That's not. But your concern is genuine. Is not the case. Yeah. So we can make it more mathematically correct with more algebra. It will take some more time.
So isn't the precision we require is arbitrary? How much we actually want the precision?
Yeah, so the number of runs will depend on how much precision you want.
And
How,
requirements
how much sure you want to be about that you have found the answer. That whether you have actually found the R and not something that is that if you how sure you are that you have actually found the real order and not a multiple of it.
And isn't it related to the cost of order?